I am going to jump into this discussion of properties and property-based testing, and more broadly within the enterprise of the broad pursuit of specification-driven development. So we started to talk last time about specification-driven development and property-based testing. And I noted the primacy here of a draft specification early on, with generative AI often being used to refine that specification, but understanding better what you're seeking through the specification. Being specification, right, is giving some information to the AI system about what's being sought, but there may be almost inevitably, there are some ambiguities, there's some lack of clarity, and GenAI can help you identify those things. But GenAI can use this sort of specification to create code, and generally you're going to iterate on that code, including with property-based tests that are created in parallel with it. And so the idea here is that you're going to be working to put in place tests that evaluate properties associated with this specification that you've created. Properties that should hold given what you want for this area of the code base. Maybe it's an API, maybe it's a class, maybe it's a function that accomplishes some key task. So you're going to be creating property-based tests, you're going to be refining those potentially with AI feedback, and the generated code generated by GenAI, beyond having a separate feedback loop as you're adjusting it to your specifications, you're going to be able to combine that with property-based tests to generate random inputs. Remember, property-based testing stands in contrast to example-based testing, right? We spoke about this before from when I was just about here on Thursday, right? So with example-based tests, this is what you've been writing for most of your career, right? You have some code and you write a test that involves giving that code some sort of input or sequence of inputs. Maybe it's in the form of some particular numbers and it gets out a number. Maybe it's in the form of you give it a file to process and it gives some results from that file. Maybe it's in the form of user input actions. It's a sequence of actions, which is another type of input. Maybe it's just defined by a gherkin and you get out some specific result from those actions. The point is, you're running the code traditionally with example-based testing on specific examples. Do you get that point? It's like specific input, right? You say, I'm going to take the square root of 4 and see if it gives me 2. I'm going to take the square root of 2 and see if it gives me 1.41, etc. Right? I'm going to take the square root of 3 and see if it gives me 9, see if it gives me 3. I'm going to take the square root of 0, see if it gives me 0. Square root of 1, it gives me 1. I think you understand the point. And maybe that square root function is designed to throw an exception when you give it a negative number, and you might test that as well, that it operates correctly, handling certain error conditions. But the point is, those are example-based tests. You're giving it particular numbers. You get that? And it gives you a result. The gherkins you write out are giving particular things to the system, and you get particular results out. If you give it a file, you give it a specific file. You get that point with example-based tests? This is different. And this generating random inputs is where you really see a divergence. It's divergent because instead of giving it a specific input as part of your test, what your test is a general recipe for evaluating, does the system achieve this property, realize this property? Does the property hold for any input? Do you get that point? So the property-based test is taking input given to it and evaluating does the property hold when I run the system on this input. Do you get that point? Key point. So what's going on here takes advantage of that, right? It's generating random inputs. This property-based testing cycle involves generating random inputs, not pre-specified inputs, not inputs that you choose, inputs that are given to you, and therefore often that you didn't anticipate specifically. Generating random inputs, feeding them into the property-based test, which evaluates does the system run properly on it, and it sees if that property is realized. Does the property hold? We're going to talk a bunch about these properties, give lots of examples. And if it doesn't hold, if insufficient tests pass, you're going to go back and modify the code base. If you deem it as having passed all the tests, or a sufficiently large or significant enough subset of them, 95% of them or what have you, that it meets your criteria for success, you may move on and put the remaining bugs in the issues base and start moving on to other aspects of generating additional code. Do you see this point? So this is a specification-driven development scheme where you're starting with specifications, you're refining them, you're using the specifications to communicate with GenAI to generate code, modify the code, and you are putting into place property-based tests that with GenAI help are being used to test the system on randomly selected inputs, which is a stronger guarantee and offers much more coverage than example-based inputs. And what we're going to see is that this extra flexibility, the fact that this test can take any input that's legal and run the system on it, any appropriate input that you want to test it on, and it will run it. By legal, I don't mean that the system has to view it as legitimate input, user input, or anything. But the fact that it can allow that it has that flexibility to handle a vast array of testing this property under different conditions, different input, that lets the system track down the sources of problems more easily through a process called shrinkage. Yes, Theo.
Just a question on the random inputs.
Yes.
So if we say it's sufficient enough for the test to pass, does it have to run on a statistically large enough amount to say I'm comfortable with saying this passed the test? Or you have to run the test multiple times?
You're generally running the test multiple times on a sizable number of inputs. And if you ask me, how big exactly does it have to be? Are we trying to achieve some statistical significance? And the answer is no. You actually want to achieve something stronger than statistical significance. Statistical significance would determine, are the results statistically different than what would be achieved by random inputs? Is there some statistical pattern that holds that's different than random inputs? You want a very specific pattern. You're trying to make sure that the system on lots and lots of random inputs passes each and every one of those. Like it actually passes them. It's not that, it passes most of the time in a way that's more than random, because you're not trying to determine is your system flipping coins, randomly. You're trying to make sure that this thing runs correctly on a vast array of inputs, right? And if it doesn't run correctly on a vast array of inputs, if there are certain files where it just hangs, or if there's other cases where it crashes on certain sequences of user input, or if there are some cases where it gives the wrong answer on certain arguments to this function you're testing through property-based testing, you want to go and figure out, why is it not giving the correct answer? Why is it hanging? Why is it crashing? Why is it not giving the correct answer? Does that make sense?
Yeah.
So that's what you're doing in this process. The fact that it's random inputs takes you out of your comfort zone where you give it inputs where it's working, because that's the classic problem with unit tests written by developers, isn't it? Right? We test our code sympathetically. We test our code to prove that it works. We say, look, Ma, it works. right? It's working. And it often forces your thinking into a kind of tunnel vision where you're thinking about certain cases where you wrote this code to handle. It's like you're showing that you're showing it stuff. You're showing that it works and you wrote good code. But when you're generating random input, you're getting out of your tunnel. You're getting out of the inputs that you anticipated necessarily, and you're trying inputs that may be from left field that you didn't handle, but it needs to be, or that you didn't think about, but it needs to be able to handle. And that's a good challenge. But the bigger picture here is by decoupling the tests, the fact that you're not doing example-based testing, that you have to handle a vast array of inputs, lets the AI system in the shrinkage procedure zero in on parsimonious, like judiciously selected, small sets of inputs, minimal sets of inputs, you can be forgiven for saying, that generate the failures. So it turns it from being, you have to undertake this long and tedious gherkin over 2 hours with your Oculus system to create this error, to you can create it in 30 seconds, boom. And that's a big help because it lets you zero in on the problem much faster. It gives you very material help for rooting it out, and then allows you to quickly test, have we really solved the problem that we think we have? Because the statistics are not good there on how often when we try to fix a problem, we often make other mistakes. I think there are some statistics, I used to present them in class, and I have them in some of my slides, and I could drag them out, but it was something like, if you're modifying in response to a bug, this is called the fault feedback ratio, the fraction of bug fixes that introduce another bug. Anyone want to guess what it is for something like 10 lines? If you're modifying 10 or fewer lines of code, roughly what fraction of the time do you introduce another bug? Roughly. 90, sorry?
15%?
Yeah, something like that. 20%, something along those lines. 15 to 25, somewhere in there, I think. May depend on language, some may depend on experience of the developer, but it's in that range. May depend on the legacy of the code base, right? Like, is it dusty duck code? Is it really old code? Is it code you understand very well? But it's a significant fraction, right? It's not like 1%. It's not 0.5%. It's not most, but it's a large enough fraction that you got to be careful, right? Because quite a fraction of the time you think you fix it and you don't. And another problem comes up. In property-based testing, having these nice crisp ways of zeroing in on things can help you track those down more easily, help you test the system in areas around this defect that was found. When it's over 50 lines of code, you want to guess what fraction of the time you introduce new bugs? Large majority. No, it's more than 50%. It's like 75%, 80%. You think you're fixing it, you're actually introducing more bugs. And the problem is those bugs, the one you're fixed, you knew about. The ones that you introduced, you don't know about. And it may take a week, 2 weeks, 3 weeks, or longer till you find them, right? The dwell time of those bugs could be significant. And meanwhile, you don't know about them. So you may try to ship code, right? You may say, oh, it is ready. ID 4 is going in. And only later do you find that it went in with a grievous problem. Okay. So what is property-based testing? Look, what you're doing is you're putting in place tests that evaluate whether code satisfies certain properties, right? Wonder what people, okay, it'll be interesting to see if people come back. I'm disturbed when people, I don't mind people leaving class for a few minutes, you just watch me, so that's great. Take your phone call if needed. What I don't like is people leaving after they know there's not a pop quiz.
Oh,
So I keep my eye out for this. This is part of Santa's knowing who's nutty and who's nice. Okay. So property-based testing uses code to evaluate whether code satisfies certain properties. We're using code, that's why it's executable specifications, right? We're writing code that checks whether a property holds. We run the system on certain input, or this part of the system on certain input. Do you get that point? Great, back, okay. So each test takes inputs or sequences of inputs, right, and evaluates whether a certain property holds. We saw that last time. We're going to jump into it, right? And then you are iterating of random inputs to see if that property is going to hold. You generate random test cases that should be pointing at this line, and you'll be evaluating whether they hold, and with eye towards finding cases where it doesn't hold. Okay. So what is a property being tested? Well, it's some characteristic of the system that you can count on that's inviolably true. It is testing some aspect of the structure of the system. We talked about that before. And if the property fails, it's not operating properly. So we gave some examples of this before. You'll remember these. I'm not going to go through them, in detail again. But if you have a string and you reverse it and then you reverse it again, you get that original string back, right? If you basically have S is a subset of T and T is a subset of U, then it follows that S is a subset of U, right? That's it, an aspect of a property. If you concatenate any string with the empty string, you get that string S back, right? In either order, right? You concatenate string X with the concat of string Y and Z, you get the same thing as if you concat X and Y and then Z, right? We went through these last time. I'm not going to belabor them. But I do want to emphasize these bottom ones. Like, by design, this is not necessarily mathematical properties. The above are specifying mathematical properties, and those are an important subset. But there are also things you build into the system. Like, you may have certain guarantees that you are trying to enforce, like the dictionary that has a symbol lookup never has a null entry in it, right? It's non-null keys in it. And you want to guarantee that, right? Or an integer passed into a function as non-negative values, right? Or that its return value is non-negative. So you can, like, your design may enforce certain properties, that there's no duplicates in some array, or there's no duplicates in a hash table for keys or what have you. Okay. So I noted that this is kind of a form of executable specification. You are enacting the specification that the property holds. Like, you are, by testing it at runtime as part of your tests, you are enforcing this rule that the property holds. It's like, that's why it's called an executable specification. The specification is this property holds, and you are enforcing it by making it so, by testing it. Do you get that point? That's why we call a property-based test a kind of executable specification. It is saying this property holds, and I am enforcing it. I am confirming it by confirming it for any of these inputs you give me. Do you get that point? Yes. Yes. Okay. All I can see is like slight vacillations in heads. So it would be nice. And, if some of that head vacillation could be because people are so tired they're going to sleep, right? Especially with my lecture. Maybe I better wave the ruler around more. Here, I'd like some feedback, even if it isn't of a riotous sort. Okay. So here we're automatically evaluating this, right? And we are using the same property-based test on different inputs, randomly generated, yeah. And we are zeroing in through this shrinking, or so-called reducing is another synonym used for it, on minimal sets that trigger the failure. And that can be done by these properties-based testing environments and by GenAI. And that can help with test reproduction and debugging. Okay. Traditionally, the biggest challenge for people using property-based testing is learning to recognize properties. So I'm going to spend a bit of time on it. Those ones I gave a few minutes ago are illustrative, but I want to give some more ones in just a minute. I do want to comment, though, on something I didn't have time to really comment on substantively last time, which is property-based testing and more broadly specification-driven development have a lot of tools to support them now. There are a staggering number of libraries for property-based testing across many languages. And this is not even all of them that I'm listing here, but it goes down and lists the kind of granddaddy of them all. Well, it's actually off the bottom called hypothesis. No, it's here, hypothesis. And that's actually not the granddaddy in Python, but it's perhaps the most prominent one of them all. It's a significant fraction. I think it's like 5%, maybe between 5 and 10% of Python users that rely on hypothesis for property-based testing. So it is actually a significant penetration in that community. And one of the points of this lecture is that it's going to be a growing fraction as AI techniques enable these tools more and more. But you pick your language. Some languages have more than one, right? Java is 3, Haskell is 3, Kotlin is prop check, OCaml is 5, etc. So there's a wide variety of types. One thing that's not to be overlooked here is the fact that most of these not only support property-based testing in a certain language, but they also provide ranking techniques, these techniques to kind of reduce the input to reproduce the error faster and faster and faster. So they provide a way of kind of zeroing in on what particular thing about the inputs is triggering the error. That's what you get when you write the property to work with any number of inputs. You can cleverly find the specific minimal set of inputs that will trigger it. You get that point? Right? Whereas if you write tests for hard-coded examples, you give it square root the number 9 to take the square root of it, you don't get that ability. This is part of this ability is writing the test to work with any number of different inputs so that you can zero in on just the minimal inputs that will trigger the problem. So this is this notion of shrinking. And you see the vast range of implementations of property-based testing, of these property-based test frameworks support this. Moreover, some support state machine testing, which is a declarative way of characterizing like how the system should behave. You could call this and then you call that, and then you call this third thing. What should it give back based on the earlier inputs? It's a very powerful technique. And I highlight that not because I'm expecting you necessarily to embrace all aspects, but because these frameworks are getting very sophisticated in being able to test things that involve like multiple calls and trace through those multiple calls and see if it returns a good result. Okay. So property-based testing is not a research activity. Like this is relied on by developers across a vast number of different languages. More than that, there are frameworks. And I particularly want to highlight the Hero framework because this is specifically AI-enabled. Framework for specification-based testing. It is, for specification-based development that allows you to take specifications, refine specifications with generative AI help, and engage in property-based testing with those. So it is an AI-enabled tool that works with you to achieve building out software to specifications and testing that software with property-based tests. It helps you build those property-based tests, etc. Antithesis is another extraordinarily popular platform that includes property-based testing, simulation of the system, generating inputs. It's an automated testing system that supports this broad range of testing. For web apps, Team 1 comes to mind here. Quickstrom is property-based testing framework for web apps. Okay. Yes, I see a hand up and we.
When you were talking about state,
Yeah.
you like an example would be like finding a column or anything like that.
Yes. Yes. So that would be a classic example of something that is a state machine. But what I'm talking about here is more subtle than that. Okay. So I mean, it's a great example of something that's state-based. But a lot of software, I mean, most software exhibits state-based properties. So if you call off to things in an API, typically earlier calls will affect the behavior seen from later calls. Unless it's a functional system where you're calling off and it's computing things back in a very direct relationship, which are very powerful systems and can be used for like web-based development. Putting those aside for a moment, most contemporary software is written in a stateful fashion. So that if you're using an API, you call off to this to, put this certain data in the database. You call off to that to, update these other tables to reflect that data. You call off to this third thing to perform a query. And what you did in the first two steps, inserting the data in and recalculating some things elsewhere in the database to reflect it, will influence what you get back on the third one. That's a state-based system. And what these systems do, Leaf, these state machine-based systems, they give you the special language or special constructs for specifying that declaratively. You can say, I expect this to be the behavior elicited when I call this. I do that then and call the third thing. What do I expect to get back? You can write formulas with it. You can give general rules with it. And you can specify that in a way that can then be tested by the property-based test. So that can use constructs like you are saying. So quantity state automata are a sort of classic model of state-based computation. You're in a certain state, you get certain inputs, you move to another state, and often you have some sort of output that comes, you emit things in a certain state. That's a kind of model of state-based computation. And these models are, these sort of state machine models can have that sort of flavor. They provide a way of saying, like, what abstract behavior do we expect out of the system? I shouldn't say abstract behavior. What specific behavior do we expect out of the system when you call it this, and this in succession? What do we expect out? So you can test it, okay? That's what state-based testing frameworks do. They give you a really crisp way of saying what behavior do we expect from this kind of sequential multi-step calls. Okay. Right. Okay. So I gave some examples before of what I called algebraic properties. And here I want to talk about that a little bit more. But I really want to get to properties on interfaces, properties that involve like classes or modules. But I'll give you a few more of these to give you the flavor. They have an elegance that's undeniable, and they're very common in particularly certain types of systems. So one thing we talked about before, I think it was Logan F. Who brought up who showed me some code from 2.14.
Yes.
You folks had written a little thing that took in a hash table or dictionary of some sort, and you could perform a filter according to some criteria and get back a resulting hash table or dictionary as a result.
Yeah.
And so here, if you started with one such hash table or dictionary, I'll just say dictionary, and and you have some criteria and you filter it down, you get another. If you applied that same criteria again, you would get back the same one you got the first time because it wouldn't change. It wouldn't need to change. You haven't filtered anything more out. The results of the first call gave you the subset of that dictionary that met this criteria. And so applying the criteria again by filtering by it won't change it at all. Everything in there already meets that criteria. I'm talking about the same criteria, exactly. So this has the flavor of something that Tyler identified as idempotency, right? Like we do it twice, we get the same thing, same results as if we do it once. Tyler pointed that out. That's called idempotent. Same thing with apps, right? Remember we saw this last time, like if we have a certain number, right? Say a double precision number, maybe it's -3, and we take the absolute value, we get what? Yeah, the absolute value -3 is 3. Thank you. Put me on one. Yeah, good. 3, and if we take the absolute value again, we get 3. Yeah. So the point is, applying it twice is the same as applying it once, right? By contrast, there are some things where if you apply it twice, you get back to the original, right? Like we saw this before. Remember when we were talking about reversing, right? Reversing a string, right? Reversing a list is the same, right? If we have a value, we take its negative, and we take the negative again, we get back to that original value, right? That's different. That's not idempotency. It's not you do it twice, you get the same as if you do it once. No, this is you do it twice, you get it back the same as if you did it 0 times, right? You got that? Same thing with swap, right? If I have a pair and I swap it, so the first goes to the second to the first, then I swap it again, then I'm back to the original, right? There are some though that are other types of properties. For example, transitive properties. So if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. Thank you. Thank you. We said it earlier with subset, right? S is a subset of t, t is a subset of u, then s is a subset of u. Thank you. Those are transitive properties. We have sort of associative properties. If I take plus of x and with plus of x of y and z, and it's the same as plus of y and z, right? So there are these certain classes of properties, and I could go and break these up, but in fact, I colored them to give a flavor of kind of grouped ones, right? And they come up in all sorts of guises. They come up with strings, they come up with lists, they come up with vectors, right? If I add a vector to a vector of zeros, I get back the original vector, right? If I add a vector v to a vector or to a plus of, to the addition of w vectors w and x, I get back the same thing as v and w and x, right? Or then z. I said x, what not to say z. Etc. These are all sort of emblematic of certain types of algebraic rules that apply across many types of inputs. And as I showed here, and as young Logan demonstrated, like these can apply for higher constructs. It's not just for lists. It's not that these don't apply once you get to something bigger than a string or list. No, they apply all around. They apply all around. They apply in many cases on larger structures. And for simplicity, I'm showing it on simple ones, but you should be looking for these for your types of structures. Okay, we'll see them in just a minute for example, with interfaces. Okay, we're going to move beyond a single function. We're going to look at interfaces. We're going to look at classes or modules here. Okay, and what you'll find is these things appear all the time in that context. It's not just these little piddly functions. You think, oh, come on, how often do I write swap or whatever? No, these things occur in your structures, and I'm looking for you to root them out. And if you don't, I will, and ask why you didn't. Okay, so let's talk about specifications. Excuse me, this is really property-based testing with these these interfaces, okay? We're going to be looking here at properties here that apply to interfaces. We will also be talking about formal specification at this level, but I won't be dwelling on that today. I'll be talking more about that on Thursday. Okay, so here's a stack. Here's a stack. Folks know what a stack does, right? We've all seen stacks many times before. You know who, for decades, had the leading algorithm for the pancake flipping problem involving stacks? One Bill Gates. As an undergrad, he found the world's fastest algorithm for doing pancake flipping involving stacks of pancakes. That's before he went and dropped out. But he has a paper to his name, William Gates, this one that for years was the leading algorithm, for decades, actually. Okay, so here's a stack worthy of buildings. Okay, so you have a stack, you could push, this is a stack of those, okay, for simplicity. We can push an end, we can pop an end, and we can ask for the size of the stack. I'm just going to put a few things down here to keep it simpler to talk about properties. Now, you notice that, like, for pushing, I say it requires none. There's no Stack Overflow, despite the website name. When you push something onto the stack, one thing that changes is the size of the stack. That's an indication of this is equal to the old size plus one. Pretty clear? Yeah, I could have called this depth. Maybe that would have been a better thing to call it, right? When I pop it, I require the size be greater than 0, right? The precondition is the size is greater than 0. And if that's the case, the new size will be the old size minus 1. Are we clear on that? Again, you could call it depth if you want, and that would probably be a better name. Okay. So here are some properties. If I push something, now here you'll notice that I'm actually needing, like, these are stateful operations, right? Like, I push, and it's not that I get back a new stack. Word only so, word only functional. Here I push, and the state is updated. It's a side effect, right? As Purity said some classes ago. We've undertaken a side effect. Int that gives a side effect. It's not like we get a stack back. We clear about that? So when I list these properties, they're going to involve several stateful computations, several side effecting computations. I start with a stack S. Any stack S, give me a stack, any stack, right? I push a number onto it, on some number n, right? And I then pop it off, I have to get that number that I pushed off. You see that? So that's a problem, right? It may not be quite as nicely written as reverse of reverse is the original string, but it's a property of this interface. Note we're looking beyond one function here, right? It's not like with reverse of a list, L, it gives us back L. That was just with one function. I was starting with those for simplicity, but now you'll notice I'm using multiple methods here, right? Push, pop, do you see that? So your mind should start going like, what other criteria? Well, we'll go through a few and then I'll give you an example, right? Or then I'll ask you to give you a little challenge. Okay, look, if we get the size of the stack and then we push a number onto the stack, the resulting size should be the original total, right? That kind of comes from the post condition, right? Similarly for pop, right? But here's something that's not directly specified in the post condition. It's not appearing in the post condition. Here, it doesn't say anything about the post condition. That, I mean, push, it doesn't say what's pushed on, right? Like it could push on every time I put something on there, it could push on, 3, right? And we would be none the wiser from this specification. But here for the properties, if I push M and then I push N and then I pop, what should I get back? So I can do that again. I just stack. I push M onto it first. and then I push n onto it. I shouldn't have put that on dot there. I should say push m semicolon s dot push n. So then I push n on, but I pushed m first, then n, and I do a pop. What should I get back? N, right? I should get back n. If I get back n, there's a problem. There's a wee problem, right? This ain't no stack. I don't know just what it is, but it ain't no stack, right? If I push m and then I push n and then I pop twice, what should I get back? M, right? Do you see how these are properties? Do you see how these properties are not entirely specified by what's given in these preconditions, postconditions as stated? As stated. Now you could reasonably ask, could I formally define these in more detail that would specify it? And that is indeed possible. But you can also see that this is a convenient set of properties that could be tested in a property-based test. For any stack, you give me an M, you give me a stack, you give me an M, you give me an N, and I could test that this second to last one holds, right? I could run it, right? And I could see, does it hold? Does that property hold? That involves more than one type of operation, pushes and pops. But it's a property of this structure. It's a, it's one of the inviolable rules of the structure that this holds true. It's the very nature of stackhood dictates being a stack. Stackness in life dictates the second class. True or not? Say it is so. Yea, verily. Yes, and the second and the stackness also guarantees this last one. Do you got that? Do you appreciate that? I should say, do you understand it? I hope you also really appreciate it. Oh man, that is good. But hope springs eternal. Okay, the crowd is not going wild. Let's move on to the next one, right? Okay, let's get this out of the way and let's get my image out of the way to add insult to injury. Okay, so here we are. We have an integer set. This integer set lets us do a bunch of things. It allows us to ask, does the set contain a given integer? We get back yes or no. And you can read the informal specification. We could say, if we insert it, it requires. Now watch this. Watch this trick. Sorry, Antoinette. No, so very importantly, the requires here says not have. So what is this saying? Like, if we're going to go insert X, what's the precondition that we what? Don't already have it, right? In fact, I didn't even hold through to that in the properties. I should. Here we elected to say not has, and what we're doing is we're actually calling has. So as part of the precondition, we are calling this function, right? We're allowed to do that. These functions have to hang together. Whatever insert does, it can ask, well, not has to be the case. I screwed up in the properties because I was not assuming that as a precondition. I was assuming it wouldn't actually require, it would allow me to call it multiple times. We'll come back to that. But this ensures after it's the case that has is true. Do you get that for that post condition? Like whatever insert does, after if you insert X, after it runs, X has to be in the integer set, right? It has X, it has to be, pun intended. Okay. And similarly, like remove requires nothing, but it ensures not has of X. Like after the post condition is, it no longer has it. You get that? Okay. A subset is something that asks, is this integer set a subset of another? And you can take the union and get of this one with another integer set and get another integer set. Do you get that? Okay, now put aside this not has because I screwed up and I was assuming that it wasn't enforcing that, that in other words, that precondition wasn't there. There'll be fewer properties to test if it were there. But here what I say is like a bunch of these still hold. Insert X, if I have a stack, excuse me, integer set, and I insert X and then I remove X, the size should be back to the original size. I screwed up. I should have taken the original size and checked if it was the same as the original size. The point is that here inserting and removing should leave the size unchanged, right? Do you get that point? If I insert and remove, it should be unchanged. If I insert X twice, counting on that precondition, if I insert twice and I ask for the size should be the same as doing one. And idempotency, it should be the same as inserting it once, right? If I remove X and then I remove X again, the size should be the same as if I just did remove X once. You got that? And here's this thing very similar to what we said earlier, the transitive property. If I say is S, if S is a subset of T, and T is a subset of U, then S is a subset of all in one voice, like the Greek chorus. S is a subset of you. Yes, okay, you bring joy to my heart. The Greek chorus is revived. Okay, excellent. Okay, and if S is a subset of T, then T size is the same as if I take the union of S and T, right? Think about that. If S, gotta get out my pen again. Maybe we'll do a different color this time for chromatic diversity. Here we go. So if S is a subset of T, right? S is a subset of T. So here we have S. So now I got to do this to like two colors, right? Okay. Make sure I don't forget this. S is a subset of T. So we have S here. We have T here is including S. Then if I take the union of S and T, then it's the same as the size of T. You got that point? Okay. I could further write a test where if I say S is a subset of T, then it means everything. So everything for which every integer for which S has that element is T also has that element. Do you get that point? So these are some properties of integer set. Do you appreciate these properties? Yes, Tyler, speak on.
Yeah, the other question about problem-based testing.
Yes.
If the random input does not violate the preconditions, or yeah.
Yes, you should in general. So you're going to want to, unless your code has defined error handling for those preconditions. Okay, like generally, you know, when we think about a method or function, it can only do its job if its preconditions are met, right? So it doesn't make sense to say like, throw you a curveball, here's something that doesn't meet your preconditions, unless there's defined decision, which I salute if there were, but it's not required, that it have error handling for all the things for which its precondition does not hold. If it handles the error, or if it throws an assertion that you can catch, that would be a good thing to check, right? If it's supposed to throw an error, or if it's supposed to throw an assertion failed exception, I should say. If it throws an exception, you can, if you can check that, great, check it. Do you understand my point? Okay. Other questions? I could see your yes, Martin.
Why definition of union, but no definition of subset in the insurance column?
Definition of union, I mean here? like, why do I say, like, spell this all out and I didn't do it here? Well, I do it here, right? I say returns true if this is a subset of S. Here I sort of write it out in, it just happens to be a longer specification. If you're asking, like, why isn't this one as long as that one?
Is there an expectation for us to define things like subsets?
Not necessarily. These are little examples to get you thinking about how you could use property-based testing in classes. Because generally speaking, look, your classes are going to have some structure. Like, you're going to ask things of them and get results back. You're going to maybe set certain things, and you can do gets of those things, and whatever you set it to should now be what you get from it, etc. You may ask it to do some sort of update, and you expect that having updated, if you ask for something, it'll give you a certain value. And I'm trying to get you to think about how you can test multiple types of methods in the same function or functions, excuse me, in the same class, or functions in the same interface together. Like you can test that they play together nicely, right? That if I insert something and then remove it, the size remains unchanged. That involves 3 different methods here, right? But they have to play together consistently. However they're defined, whatever their implementation, they have to satisfy this rule. Does that make sense?
Yeah.
And you should be looking in your code bases, not for like, is there a subset or union, but like, what are your kind of, what are your methods? And how do they have to play together nicely? Like if we do this and do that, we should get back this sort of thing. Does that make sense? And maybe it's not, it's exactly equal to, maybe it has to be greater than or equal to this certain value. So maybe you add in some things to a set, and the resulting size should be greater than or equal to what it was before you added them in, for example. Your particular cases will look different from the particulars here. I'm trying to give simple examples to build up the sort of reasoning, but I am aiming that you should be able to try to find these sort of properties with your systems. The reason I'm dealing with this is because that one of the things that studies of property-based testing find is the biggest limitation for it. It's an amazing method, but one of the biggest limitations is a lot of students, and then as they go into industry, software engineers find it, they don't have an intuition for how to identify properties. And I'm trying to teach you here, it gives you some pointers on how to identify properties, okay? I'm looking forward, starting Monday, to reviewing your ID4 code bases, and I will be looking for these examples, and hopefully I'll see some property-based tests with them. If not, I'll say, hey, there's a property here. Like you set this and then you get that. There's something that unites them, or you set this and you call this method, then you could get, and you should always get something that's in this range or what have you. And I'll be looking for those for your code bases, okay? And if you don't find them, I will point that out and try to find them. Okay, here's a queue. So what are some properties of this queue? You know quite a lot about queues. You know your P's and Q's. So what are some properties of these queues that we could expect? So I have a queue, and I can ask for the size of the queue, the number of items in the queue. I can ask if it's empty. I can ask, I can say I want to add something to it. That's down here in the bottom. Something of E, parameterized, but that's a type of E. I can remove something from it, or I can peek at the head without removing it. What's at the front of the queue? So what are some properties? What sort of properties might apply to this? Yes, young Theo.
If I add something to it and I peek into it, we should see that.
Good, excellent. That's a great one. Yes.
So we would say first in, last out.
Yes. Oh well, first in, first out, right?
Okay.
The stack will be first, last in, first out. Yeah. Yes. Yeah. But exactly, you're exactly right. You're thinking exactly right. So it should have some sort of first in, first out property. What would that mean operationally? Like, what would it mean? If we did what, you'll get what? This, and you would expect that. What would that be? So I see a Theoian hand, but are there any other hands that could be tap map?
If you add A and then add B and then peak, you'll get A.
Exactly. Yeah, that'll be at the head. The thing that went in first, right? Opposite of what a stack would do. Use comparable, obviously comparable. Yeah. Good. Other ideas? Like are adding and removing independent from being empty, for example? Yeah. Derek?
You have like n equals like the size,
Yep.
and then you do an add, make sure that you have size plus 1.
Good. What if it's empty and then you do something? It's empty and you do if you do it, it's empty and you do a remove, then what should happen? Well, it should fail its assertion. But let's have a variant on that. If you add, if it's empty and then you add, should it be empty anymore? No, it shouldn't be empty anymore, right? That's like a property you can count on, right? On which you can count. That's it. That's just something about how queues work, right? That you can count on. It's not, all over the map and you add something you don't know, you don't know if it landed or not. You don't know if this thing is empty or if it's full. It could be anything in the world. No. Look, a queue has certain rules, certain logic to it, and you can look for those. It has certain properties. It has structure to it, and the properties point to the structure. Good. So how about something involving peek and remove? Yes, Tyler.
If you peak and then remove, it should not be the same, and peak again, the fields should be different.
Okay. Well, it could be the next thing in the queue is the same, right? It could be. But one thing that's certainly the case is if you peak and you get back a value, and then you remove and get back the value that was at the head, how should they be related? They should be the same. It should be the same. So yeah, that the kernel of the right idea there, exactly. Is there some relationship between is empty and size? Yes, Logan.
Is empty being true to imply that size is 0?
Yeah, exactly. If we have something for which is empty is true, size should be 0. Conversely, if we have something for which size is not 0, good. That's right. Good. The first in, first out property, it was a key one, and that could be evaluated. Leaf had zeroed in on that earlier, right? But if we add to the QM and add to the QN, then the peak should be M, the first thing added. Also, the remove of that should be M, the first thing added. And when we remove it, what should we get? What should the first thing be after we remove it? The other one, right? And are you starting to get a flavor of this? Like there's structure here, right? Like there's regularities. It's orderly. It's not all over the map. It's not just kind of a queue has certain defined rules of the game, certain logic to it, and you can test these things. Could you imagine writing a test for these sort of things? Yeah, adding random things to the queue and seeing if indeed these properties hold. And indeed, they should hold for a vast range of inputs, right? Regardless of whether you add 3 and then 5, if you peak, it should give 3, right? And if you then remove, you should get 3. And if you then peak, you should get 5, right? But the same thing is true as if you added, 13,001 and, 23, right? If you peak, then you should get 13,001. If you remove and then peak, you should get 23, etc. You see my point? Like, these are regularities. They're defined things that you can test. And that's what property-based testing can do. Okay, so there's a wealth of properties. And I would challenge you, and I would inveigh upon you, and I would exhort you to go off into yonder hills and find the properties in your structure, because there, in those hills, lies gold to be exploited and to support you in testing, in debugging within the age of generative AI. Thank you. Okay, well, maybe the crowd went wild that time. Thank